Hello, everyone. I'm Yuanyuan from the Hong Kong University of Science and Technology. I'm going to present our work, Precise and Generalized Robustness Certification for Neural Networks. This work was done when I was visiting ETH Zurich, and it is a joint work done with my two supervisors, Shuai and Zhendong. The precise robustness certification can be illustrated using this figure. Given an input X and a mutation, the certification first represents all mutated inputs X prime as the input space I, and then it checks if the neural network has the same prediction for the original input X and all the mutated inputs X prime. In practice, neural network robustness certification is sound, which means if the certification succeeds, then all mutated inputs must have the same prediction with the original input. Nevertheless, the completeness may not always be guaranteed. If the certification is complete, then the certification fails only when the neural network has inconsistent prediction for some inputs. In contrast, for incomplete certification, the input space is usually over-approximated. And as a result, if the certification fails, we don't have any conclusion about the result because the failure may be caused by the over-approximation. There are many diverse input mutations in reality. For simple pixel-level mutations, they have explicit mass forms and the resulting input space is linear. That is, we can directly get a precise input space representation for these mutations. Such simple mutations are also the main focus of most previous works, and currently, sound and complete certification can only be performed for these mutations. There are also some more complex mutations such as geometric mutations, including translation, rotation, and filter-based mutations such as blurring and adding weather filters. These mutations also have explicit mass forms, but their resulting input space is nonlinear. To certify robustness towards these mutations, the input space is usually over-approximated, and only incomplete certification can be delivered. There are some special mutations that do not have explicit mass form, and accordingly, their input space is nonlinear. Examples include style transfer, perceptual mutations such as changing orientation, postures, and some local mutations such as opening mouths, closing eyes. We denote these mutations as advanced mutations because they are never studied in neural network robustness certification. Our work is orthogonal to existing neural network certification works. It aims to solve the input space representation problem. It is precise because we aim to obtain precise input space for diverse real-world mutations. And our work is also generalized because we aim to support the advanced mutation I just mentioned in previous slides. We also aim to implement different mutations in a unified manner and incorporate our techniques into conventional certification frameworks to enable different certifications such as complete certification and also the quantitative certification. Our unified implementation of different mutations is actually inspired by generative models. Intuitively, given a collection of images, a generative model maps them into the latent space. Then, when mapping back from the latent space, the generative model can generate infinite images by interpolation or extrapolation. Thus, we can implement data-driven mutations using generative models, and more specifically, we can extract mutations from diverse images and represent different mutations as different moving directions in the latent space of the generative model. If this is possible, we can apply the certification on the composite neural network F over G. Since all mutated inputs of one mutation are represented as a segment, the complete certification can be enabled for those complex and advanced mutations. But unfortunately, the generated image GZ changes arbitrarily with Z. To make generative model suitable for precisely representing the input space for different mutations, two requirements must be satisfied. First, continuity. When performing mutation, the generated model GZ should change continuously with Z. And the second, independency. When mutating the image GZ into another image GZ prime, the direction pointing from Z to Z prime should only correspond to the expected mutation. Let's consider this example. When performing rotation, as you can see here, the mutated images should change continuously with Z. And also, when you rotate the image, the scale of this image should unchanged. And similarly, if you want to rescale this image, the rotation angle should always be the same. With these two requirements, we can ensure that the segment connecting Z and Z prime will exclusively correspond to all mutated inputs between GZ and GZ prime. The continuity can be formally represented in this way. The distance between GZ and GZ prime is bounded by the distance between Z and Z prime. To achieve the continuity, we can bound the Jacobi norm of the generative model. Here I only show the conclusion. You can find the detailed derivation formulas in our paper. We call this process as the Titan operation, as shown here. Given a series of gradually increased Z, in the original generative model, GZ changes arbitrarily. To regulate the generative model for any adjacent Z, we can minimize the distance between their corresponding GZ. An example is given here, and as a result, all the GZ will finally change continuously with Z, as shown here. We ensure the independency from two aspects. First, we represent different mutations as orthogonal directions in the generative model's latent space, such that mutating certain properties in the input will not affect other unrelated properties. And second, for some local mutations, such as opening or closing eyes, before performing the mutation, we project the corresponding direction into another direction that does not change the remaining regions in the input. This way, we can ensure that only the target region of the local mutation is changed during our mutation. In our evaluation, we evaluated our enabled mutations. We summarized some key findings. First, for perceptual mutations, the number of enabled mutation is affected by the resolution of the generative model's training data. So use higher resolution training data for your generative model. And in addition, since our mutation is data-driven, so the enabled mutation and their maximum extents are decided by the generative model's training data. More concretely, for example, to enable rotation within 30 degrees, some of the generative model's training data must be rotated at least 30 degrees. But to enable representing all mutated images within the 30 degrees, it is unnecessary to cover all rotation angles in the training data because the generative model is continuous with our regulation. Here are some examples of our enabled mutations. As you can see, different mutations are independent and they change continuously. We also incorporate our techniques into conventional certification frameworks. For example, we use our tool to perform complete certification for geometrical mutations over different neural networks and study their robustness. Overall, our techniques reduces the cost from exponential to polynomial. While certifying the composite neural network F over G increases the number of layers in the target neural network. But because the inputs to F over G is a segment rather than a region as in previous works, the computing cost is actually reduced. And we also find that by cross-comparing the convolution layer and the fully connected layer, the convolution layer can enhance the robustness towards geometrical mutations, and also increasing the depth of neural network brings better robustness. And more importantly, data augmentation, which randomly apply geometrical mutations to a model's training data, can also enhance the robustness. We also incorporate our tool into the recent quantitative certification. The quantitative certification is more fine-grained. It gives lower and upper bound for the target neural network's robustness. It requires that inputs to a target neural network should be represented as one segment or a chain of segments. this is true in our setting. We analyze the face recognition neural network and find that the neural network is more sensitive to mutations over some key facial attributes such as eyes. And in contrast, mutation of the global properties like face orientation can hardly change the neural network's prediction. We also perform certification over different types of mutations and study how they affect neural network's robustness. In general, geometrical mutation is not a major concern to modern well-trained neural networks. And artistic style transfer and filter-based mutations are very sensitive, are very effective to change a neural network's prediction. This result is actually consistent to observations in some machine learning studies, which pointed out that modern neural networks are biased to textures in images. That is, these neural networks usually rely on textures to make predictions. And artistic style transfer and filter-based mutations change textures in images. And also local mutations are effective to flip a neural network's prediction because they usually change some key local attributes. To summarize, in our work, we implement different diverse mutations in a unified way, and our approach is based on generative model. But usually, the image generated using generative model change arbitrarily. To make generative model suitable for neural network robustness certification, we propose two requirements: continuity and independency, and we also give the solutions. We then incorporate our techniques into conventional certification frameworks and study the robustness over different neural networks, and also study how different mutations affect the neural network's robustness. Thank you for listening. I'm open to any question.